After studying this module, you shall be able to know about bicyclic molecules, learn about the stereoisomers of decalin, understand the conformational analysis of cis and trans decalins, decanols as well as decalones, and identify different types of strains in the conformations of decalins. And finally, you will be able to predict the most suitable and energetically favorable conformation for decalins in natural compounds. Compounds with two rings fused together are known as bicycles. Bicyclic systems can be either fused or bridged bicycles. If you look into the following figure, you can see two types of bicycles. One are fused, which share the two adjacent carbons, while the bridged rings share two non-adjacent carbons called the bridgehead carbons, and there is one or more carbons between these bridgehead carbons. In this module, we will be focusing our study on the fused ring systems and the category of fused bicycles, mainly decalins and its derivatives. The IUPAC nomenclature of decalin is bicyclo 4,4,0 decane. The numbers 4,4,0 represents the number of carbon atoms in each ring besides the bridgehead carbons. Since there are only two rings, therefore, there is 0 carbons in the third ring system, which carries only the bridgehead. The rest of the two rings have 4 carbons each, and hence the number 4,4,0. Decalin is also known as decahydronaphthalene because it is a saturated analog of naphthalene, and it can be prepared by naphthalene by dehydrogenation in the fused state in presence of a catalyst. The nature of the catalyst will decide which isomer of decalin will be synthesized. The synthesis actually lead to the formation of two stereoisomers of decalin, one where both the hydrogens on the bridgehead are cis to each other, and the other where both the hydrogens are trans to each other, as shown in this figure. The cis will have both the hydrogens shown as solid wedges, whereas the trans has one hydrogen shown as solid wedge and the other hydrogen is shown as dash wedge bond. Let us now talk about the conformations of decalin. Decalin has two cyclohexane rings fused together, and you know that these cyclohexane rings are more stable in their chair conformations. So, it is expected that the two fused cyclohexane rings in decalin should exist in their chair form. In fact, the scientists Sachet and Moore suggested decalin to be a strain-free puckered structure which exists in two isomeric forms that cannot be interconverted without breaking a bond. That is, they are configurational isomers, or we may also call them as distereomers. This figure shows the puckered structures of the two cis as well as trans isomers of decalin. Since both the isomers have cyclohexane rings in their chair conformation, there is no angle or torsion strain in these decalin molecules. It can also be seen from the figure that in trans decalin, the two bridgehead hydrogens are pointing in opposite directions and are both axial hydrogens. On the other hand, the cis decalin, the two bridgehead hydrogens are pointing in the same direction, both upwards as shown in this figure, and one of them is axial while the other one is equatorial. Now, let us see if there is a ring flipping in decalins as we have studied in case of cyclohexane. In trans decalin, the two cyclohexane rings are joined through equatorial positions. Now, do you remember the equatorial position in cyclohexane is always less hindered and more stable than the axial position? To place a substituent, we have seen that in last module that in cyclohexane the equatorial position does not face any steric inhibitions or any gauche interactions where the substituent is present in equatorial position. While if we keep a substituent at axial position, there is gauche interaction which makes it less stable. and hence equatorial position substituent will always be more stable. So, in ring flipping, you know that in cyclohexane it changes all the equatorial bonds to axial bonds and vice versa. Likewise, ring flipping in transdecaline would give a conformation where the two cyclohexane rings would be joined through axial bonds. However, this ring flipping is highly prohibited as it is not possible to have a 6-membered ring built with two of its bonds in diagonally opposite directions. We would fail if we try to construct a model where the cyclohexane rings are joined through axial bonds. You can see or try it at home. Thus, the transdecaline is conformationally locked as the ring flipping cannot happen. It remains in the equatorial conformation with respect to both the rings, and we represent this conformation as EE conformation. The EE transdecaline has a center of symmetry lying at the midpoint of C9 and C10 bond as shown in this figure, and hence it is an achiral or optically inactive molecule. That is, its mirror image is superimposable on it. It also has two C2 axes of symmetry, one passing through the equator and the other passing through the axis as shown in the figure. In contrast to transdecaline, which is comparatively a flat molecule, the cisdecaline is more like a tent-shaped molecule as shown in this figure. It has the convex and concave sides, which is shown in this figure. The convex side is less hindered, that is the top phase, whereas the concave side is sterically more hindered, which is the bottom phase. It is more hindered because no reagent can easily come and approach through this side of the molecule, whereas the convex side or the top phase is sterically less hindered and the reagent can easily approach for attack in this side. Although in both the cases, the cyclohexane rings are in their most stable chair conformations. In cisdecaline, the two cyclohexane rings are joined through an equatorial and an axial bond, and the ring flipping is permissible in this case, which converts one cis form into another and converts the equatorial bond to axial and vice versa. That is, the EA cisdecaline on ring flipping will give AE cisdecaline. This equilibrium is shown in this figure. The conformational analysis of cisdecaline shows that it is a chiral molecule, though it has no chiral carbon in it. It has a non-superimposable mirror image. However, a rapid ring flipping cancels its chirality and converts it into its mirror image. Thus, the two chiral forms are not resolvable due to its rapid ring inversion, and it always exists as racemic mixture. The ring flipping in cisdecaline was also supported by its NMR spectra, which shows only one proton peak, in contrast to transdecaline, which shows two proton peaks. The two proton peaks in transdecaline can be attributed to its rigidity, because there is no ring flipping possible. It is a conformationally locked molecule. The axial and equatorial protons are held in different environments and thus show different chemical shifts, and therefore two signals for transdecalines. While in cis isomer, it is capable of ring interconversion, and consequently the equatorial and the axial hydrogens face an average environment and therefore occurs as a single chemical shift for all the protons. Now let us see the energy considerations in cis and transdecaline. A closer look at the transdecaline shows that all the carbon-carbon bonds are equatorial to each other, an arrangement which leads to the flat shape of this molecule, and hence there are no gauche interactions. While in cisdecaline, there are 3 gauche interactions. Comparing it with gauche interactions in N-butane, which amounts to an increase of 3.35 kilojoules per mole for every butane gauche interactions, The total energy difference between the trans and cis decalins is therefore equal to 3 times that of the individual butane-Gauss interactions. That will be 3 into 3.35, which equals 10.5 kilojoules per mole. Thus, trans decalin is more stable than cis decalin by 10.5 kilojoules per mole. There is also an argument which says that cis decalin is less stable because of weak non-bond interactions in the concave side or more hindered, sterically hindered side of the cis decalin. So, that will add to the instability, and trans will always be more stable than the cis decalin. The number of Gauss interactions remains the same on ring flipping of cis decalin. So, we can say that the two conformers of cis decalin which we obtain after a ring flipping are exactly equal in energy, and that is also a reason for rapid ring inversion. Due to the convex and concave tent-like shape of cis decalin, the two faces are sterically non-equivalent. Look at this figure. Here, an incoming substituent would prefer the less hindered convex phase, which is more accessible and less hindered. For example, let us study the methyl substituted case. In cis 9-methyl decalin, the methyl group occupies the convex phase over the concave. However, it is less stable than trans 9-methyl decalin due to the larger amount of Gauss interactions in the latter. Because trans is a flat molecule, there will be no butane-Gauss interactions, because this methyl group will be on the bridgehead carbon that will be axial to both the rings, that contributes to 2 butane-Gauss interactions for each ring, amounting to 4 butane-Gauss interactions in all. So, this bridgehead carbons imparts destabilization equivalent to 4 butane-Gauss interactions in trans decalin, 2 with each ring, as the substituent is present to axial position. On the other hand, the cis decalin, a substituent imparts destabilization equivalent to only 2 butane-Gauss interactions, as it is axial to only one ring. Thus, in all, there are 4 butane-Gauss interactions in trans 9-methyl decalin and 5 in cis 9-methyl decalin, thereby reducing the energy gap between the cis and trans decalins to only 1 butane-Gauss interaction. Similar analysis suggests that on introduction of a second substituent on the other bridgehead carbon would increase the energy of the trans isomer even more than the cis isomer, because every additional substituent on the bridgehead trans isomer would lead to an increase of 4 butane-Gauss interactions, while only 2 in cis isomer. So, for a disubstituted decalin, the trans would be less stable as compared to the cis isomer. In trans isomer, there will be 8 butane-Gauss interactions, whereas in cis isomer we will have 7 butane-Gauss interactions, consequently making cis isomer more stable than the trans. Let us see now some of the examples of natural molecules which contain decalin as their structural moiety and their conformations. The decalin moiety normally appears frequently in natural products like steroids, terpenes and alkaloids. The molecules shown here are cholesterol, cholic acid, progesterone, testosterone and some other couple of molecules, where you can identify easily the two hexagon which are fused together, that is the decalin moiety. In these natural products, the cis isomer actually exists in a particular conformation. That means the ring flipping does not happen here. So, in these natural products, the particular conformation in which the cis isomer exists is specific to these natural products, and this happens specifically in steroids. Thus, the conformations of cis decalin can be now classified as steroidal or non-steroidal on the basis of its occurrence in these natural products. Let us now study the configurations of decalols and decalones, the derivatives of decalin. Introduction of a substituent other than on the bridgehead carbons give rise to a new chiral center in the decalin molecules. and thus it increases the number of stereoisomers. For monosubstitution in decalenes, there are two equivalent positions as shown in the figure. These are 1 or 2. So, there can be only two structural isomers for decalol, namely 1 decalol or 2 decalol. Similarly, there can be only two structural isomers for decalones, that is 1 decalone and 2 decalones. The substituent not only generates the chiral center at the point of substitution, but also makes the bridgehead carbons chiral by disrupting the symmetry in decalene. Hence, decalols will have 3 chiral centers, that is 1 at the point of substitution and 2 as the bridgehead carbons. On the other hand, decalones will have 2 chiral centers at the 2 bridgeheads. The point of substitution will not generate a chiral center here because it is an sp2 hybridized carbon where the carbonyl group is introduced. Thus, the number of stereoisomers theoretically possible would be, for decalols it will be 2 raised to the power 3, that equals 8 stereoisomers, and for decalones 2 raised to the power 2, that equals 4 total number of stereoisomers possible. Let us identify the possible stereoisomers in each of these cases. In decalones, we would first have two geometrical isomers, cis and trans, and both of these isomers would have their mirror image that are non-superimposable. That is, they would exist in resolvable enantiomeric pairs as shown in the figure for 1 decalone. Each resolvable pair in cis 1 decalone is in equilibrium with its conformer due to the ring flipping. This does not happen in case of trans decalone as it is conformationally locked. So, in all there are 4 stereoisomers in 1 decalone, that is an enantiomeric pair for the trans decalone and an enantiomeric pair for cis decalone, but each enantiomer is in equilibrium with its ring flipping structure. The conformational analysis predicts the trans decalone to be more stable than cis isomer because of the similar reasons as in decalenes. That means the butane-gauche interaction in cis would be more in number than in trans decalenes. The cis isomer has more butane-gauche interactions than the trans isomer, and 2 decalones also shows a similar stereochemistry as in 1 decalones. Now, reduction of these carbonyl group to give a hydroxyl group introduces a new chiral center, and a corresponding increase in the number of stereoisomers happens. Let us now identify the stereoisomers in decalols and predict their relative energies. Theoretically, 8 stereoisomers are expected of decalols. That means 4 pairs of enantiomers, as it has 3 chiral centers. Actually, all the 8 forms have been isolated. However, their configurations have not yet been established with certainty. Let us take 2 decalol as a representative example. It can exist as cis and trans decalol, and each isomer can have hydroxyl group either at axial or equatorial positions. As we know, the trans decalol is conformationally locked. That means it cannot undergo ring flipping. It is not possible to interconvert the axially substituted hydroxyl to equatorially substituted hydroxyl. Consequently, both would exist as diastereomers. Further, these diastereomers would have a non-superimposable mirror images. Thus, trans 2 decalol exists as 2 pairs of enantiomers as shown in this figure. One would be enantiomeric pair for axially substituted, and the other one will be enantiomeric pair for equatorially substituted hydroxyl groups. Conformational analysis predicts the equatorial substituted trans decalol to be more stable than the axial isomer due to 1,3 diaxial interactions in the latter. The cis isomer, on the other hand, is more complicated owing to its flexibility and the possibility of ring flipping. The ring inversion would convert the axially substituted hydroxyl to equatorially substituted hydroxyl. However, due to the presence of two non-equivalent phases, that is convex and concave phases, or sterically less hindered or sterically more hindered phases, there are two different arrangements for axially substituted hydroxyls, and the same is true for equatorially substituted hydroxyls, as shown in this figure. The equilibrium shown on top has axial hydrogens on the concave side, while in the equilibrium shown on the bottom has axial hydrogens on the convex side. Each of the isomers shown would have their non-superimposable mirror images to add on to the number of stereoisomers. Conformational analysis of cis-2-decalol suggests the bottom equilibrium to be more stable than the one shown on the top due to the non-equivalence of convex and concave sides. The axial hydroxyl group on the concave side would experience 1,3 diaxial interactions, making it less stable. The equatorially substituted hydroxyls in both the equilibriums have same energy, as they do not face any steric repulsions. Both the equatorially substituted decalols are more stable than their axial counterparts and hence contribute more towards the actual state of the molecule. Now let us summarize what we have learned about the conformations of decalins and its derivatives. What we have studied is decalin, which is also known as bicyclo-4,4,0-decane. It is a bicyclic molecule that has more interesting configurations and conformations over the regular cyclohexane. The fusion of two cyclohexane rings impart special characteristic to this molecule. Decalin has two cyclohexane rings, both in their most stable chair form, and thus it is free from any torsional strain. Due to the rigidity imparted by the fusion of two rings, it exhibits geometrical isomerism and exists as two diastereomers, namely cis and trans decalins. In cis decalin, the two bridgehead hydrogens point in the same direction when one of them is axial while the other is equatorial. In trans decalin, the two bridgehead hydrogens point in opposite directions and are both axial hydrogens. Trans decalin is conformationally locked in equatorial conformation, and any attempt to invert the ring would lead to breaking of bond. The two axial carbons would be too far apart to form a six-membered ring, and this is supported by NMR studies. Cis decalin, on the other hand, exhibits a rapid ring inversion. The trans decalin is achiral, as it has a center of symmetry, while cis decalin is chiral. However, the chirality of cis isomer gets cancelled due to rapid ring inversion that results in a non-resolvable isomers, which is a mixture of dextro and levorotatory isomers. Trans decalin is more stable than cis decalin by 10.5 kilojoules per mole, owing to 3 gauche interactions in the latter. The cis decalin is more like a tent-shaped molecule with two non-equivalent faces, convex and concave sides, in contrast to trans isomer, which is more or less a flat molecule. Substitution at the bridgehead carbons increases the number of butane gauche interactions in both the isomers. It increases more in trans as compared to the cis isomer, and thus alters the energy gap between the two isomers. The decalin moiety appears frequently in natural products like steroids, terpenes and alkaloids, and in these natural compounds, the cis isomer exhibits a particular conformation termed as steroidal conformation. Introduction of a substituent other than on the bridgehead carbons gives rise to new chiral center in decalins, and thus increases the number of stereoisomers. The substituent not only generates the chiral center at the point of substitution, but also makes the bridgehead carbons chiral by disrupting the symmetry in decalin. Hence, decalols will have 3 chiral centers and decalones will have 2 chiral centers that is the 2 bridgehead carbons. The number of stereoisomers theoretically possible for decalones are 2 raised to the power 2, that equals 4, and these exist as 2 enantiomeric pairs, one each for cis and trans decalone. The conformational flexibility in cis isomers, however, increases the possibility of more stereoisomers. The number of stereoisomers theoretically possible for decalols having 3 chiral centers are 2 raised to the power 3, that equals 8. These exist as 4 pairs of enantiomers, 2 each for cis and trans decalol. The trans decalol, being more conformationally rigid, exhibits 2 distereomeric isomers, namely axial decalol and equatorial decalol, and each of these distereomers further exhibits enantiomerism, resulting in a total of 4 stereoisomers in trans decalols. The cis isomer, on the other hand, is more complicated owing to its flexibility and the possibility of ring flipping. There are 2 different spatial arrangements for axially as well as equatorially substituted decalols, both convex as well as concave sites. However, they can interconvert through the equilibrium involving ring flipping.